Yo, what's up, everybody? We're moving on to from our discussions of reflection with mirrors to discussions of something called refraction, which many of you saw literally in an activity we did where we took a block of glass like this and we put an object on one side of it and we looked through the glass to see where the image of that object was. All right, and what we did was something like this. If you weren't here, we're gonna move over there. Maybe I'm gonna do this. Yeah, so we put your eyeball over here, and people looked through this block of glass and said, "Well, boy, it looks like there's a pin that we stuck into the paper." All right, so it looked sort of, well, if you were here, you were here. Now, if you look at those notes, or look at the back of your note packet where you drew this, where you drew the one ray we talked about drawing, if you continue this ray on, if you continue it through where the block is, you'll see that it does not point at the actual place where the object was. So we say that it looks like the object was there. It looks like it was, if you trace this ray back, it looks like the object was here. However, you'll see that the object actually is somewhere over like that. All right, now what does happen is that light from that object travels in the same direction you saw it traveling, but when it enters the glass, it actually does that. It changes direction, and when it comes back out of the glass, it changes direction again and hits you in the eyeball. All right, or we say it does. We say that the light refracts. All right. Now, what we're not drawing here, but what does happen, is that some of the light that hits this boundary right here actually reflects also, following the law of reflection. So if you put an eyeball here, you could see the pin also. All right. It would be dimmer because typically more, well, in this case, more of the light goes through the boundary than reflects off it. But at any boundary, both of those things can happen. For now, we're only going to focus on the refraction part. Okay, so the object is actually there, right where we circled. So you should be able to draw these rays. If you used a ruler, what I do is just do my best to make sure the ruler here sort of lines up with this. Try to do your best to make sure they're parallel. Draw this ray up here. Oops. Draw this ray up here, and then draw this one on the inside that connects the ray on one side to the ray on the other side. Okay. So here's the path that the light actually takes in the solid red line. Okay. Now we have to define some stuff. We say that in this diagram there are two what we call incident angles. We're going to relate angles that you see here to other properties of the substances that light is traveling through. And an incident angle, by definition, is an angle that a ray approaching a boundary makes with the normal, I should say. With the normal. With the normal. I said it a while ago, and I'll say it again. Anytime we talk about angles in this unit, they are always measured with respect to a normal. All right, so there are let's call angles 1, 2, 3, and 4. Two of them are incident angles. They are angles that an incoming ray makes with a boundary. Well, sorry, it really makes with a normal as it approaches a boundary. So those are two incident angles, angles 1 and angle 3, angles 1 and 3. Those are angles that an incoming ray makes, or a ray that approaches a boundary makes. And then the other ones are called refracted angles. And those are angles that a ray makes with the normal after passing through the boundary. And those are those two angles there. Okay? And what Snell's law says is that these angles have a relationship. And what I mean by these angles is, if we look at this boundary right here, theta incident and theta refracted have a certain trigonometric and algebraic relationship. Or if we look at this boundary, we can say that there's a similar relationship. And that relationship looks like this. We'll explain a little more in a minute. It says n1 sine theta 1 equals n2 sine theta 2. So we talk about the sines of these angles, right? The sine of that and the sine of that. What's 1 and what's 2? That's up to you. All right. What we'll end up writing is more probably like n air sine theta air is n glass sine theta glass. It doesn't matter 1 and 2. All right, now sine of theta, sure we know what that is, but what's this thing n? All right, well, we got to talk about what that is. So what can help is to talk about why do waves change direction when they go from one substance or one medium to another. Well, here's why it happens. There's a great applet out there. Oops. I hope it's still out there. It's going to load. You jerk store. I'm going to pause. Hang on. Okay, so here's why it happens. This applet is what I was looking for, and it shows here a wavefront. Yeah, there's a wavefront that's approaching the boundary here between two substances, or two media, medium 1 and medium 2. And we say that the first medium has an index of refraction. That's what n is called. N is called index of refraction. N has index of refraction 1. Medium 1 has index of refraction n equals 1, and medium 2, we say, has index of refraction equal to 2. And watch what happens when the light, or when that wavefront, that peak, gets to the boundary. This is going to take forever. Resume. It's traveling down here like that. You're going to see two things happen. I hope something happens. Son of a... Next step. Sure. Okay. Now, I got to explain a little bit of what's called Huygens Principle. Right? You know, it's up here. It talks about Huygens Principle. Huygens Principle says that, a wave by nature keeps propagating. And how does it do that? Well, it happens because every single location in space, whether that's literally just a location in space or a piece of actual physical matter, what those locations / objects do is when a wave hits them, they propagate the wave. All right? And you're going to see that these things, when the wave pulse hits them, they do their job by creating or becoming a source of more waves. Fair enough? Now, notice, we're showing two things. This is a reflected wave. You see the, I wonder if you can see the flickering of the image. It's so annoying. That's a reflected wave, a wave that comes back off that boundary. Here's this boundary right here. And here is a transmitted / refracted wave. Okay. Sorry, just almost fell down. Now, what you'll notice, I hope, is that the reflected wave has traveled a farther distance than the transmitted one. And in fact, if you look close, you can tell that, now notice, this is like a lot of peaks on top of each other, which is like one big peak. And this is like a lot of peaks on top of each other, or like one big peak. And notice this distance that the reflected wave has traveled is twice this distance that the refracted wave has traveled. And notice here also, there's that ratio of 2 to 1. Okay, so what that says is index of refraction has to do with how fast a wave travels in a substance. Okay, what I can do is, what I am going to do is I'm going to change some stuff. I'm going to change this to say 30. And then, how about this? I'll change it to, 30. Oops, get all this out of here. And we'll restart, and we'll go to the next step. So watch as this wave comes in here. All right, this wave that comes in, well, we see it reflect out, and we also see it go through. I'm going to go next step, and this happens. I'm going to go next step again so we can get this sort of diagram of what happens. All right, we see one, I'm going to actually go next step, and we see a bunch of wave fronts come in here in the medium 1. And we see those sources of more waves behave according to Huygens Principle and propagate the wave and do their job. And what we notice here, it's kind of a mess, I agree, right? The wave that came in going this direction as reflected coming out going this direction, right? And this behaves according to the law of reflection right there. But since this wave slows down in the second medium, what we get the wave doing is it was going in this direction, it actually bends this way and now goes in this direction. Have you ever seen a busier diagram in your life? Okay, so that's a big deal. All right, the reason that these waves change direction is because they change speed. All right, and that brings us, I hope, back to here. Why does refraction happen? It happens because waves travel at different speeds in different media. Now, if we talk about light, and we're going to talk almost exclusively about light when we do refraction, right? We say that light, I'm going to say this, light. Even light travels at different speeds in different media. There's a speed that we just call c that light travels at in a vacuum. And c is a known value, 3 times 10 to the 8th meters per second. In anything else, light travels at a speed that we'll call v that has to be, by definition, less than c. And how much less it is a function of, or is how we define what we call the index of refraction of any substance. All right, because the wave changes speed when it goes from one substance to another, it also ends up changing direction. All right, now the ratio of these two speeds is what we call index of refraction. Or we can say that for substance, remember medium 2, let me show you again. Medium 2 down here, where the wave traveled twice as slow or 1/2 as fast, and here in medium 2 had the index of refraction of 2. Right? So the bigger this index, the smaller the speed v. And that means that n, by definition, pop up by itself, is c over v. Okay, that's the definition of index of refraction. And that, where's this n from? N is from n1 sine theta 1 equals n2 sine theta 2 from Snell's law. Okay? Notice that n is just a ratio of two speeds, so there are no units. So here's a diagram like we saw. All right. Now we're going to come up with a great what we call mnemonic device for how Snell's law works. So there's Snell's law. All right. N1 sine theta 1 equals n2 sine theta 2. Now, if we just do some algebra and rearrange, we get that. Okay. Now, in the case, there are two cases. Here's one of them. One case is that n1 is smaller than n2. Well, if that's the case, if n1 is smaller than n2, it means that this sine theta 2, that sine theta 2 has to be less than sine theta 1. Or really, that means that theta 2 has to be less than theta 1. A sine function looks like this, right, in the beginning at least, and we only go up to 90 with these angles. They can only ever be as big as 90. So the bigger an angle, the bigger its sine. All right, so this says that if n1 is less than n2, then theta 2 has to be less than theta 1. So that's the case that we're showing here, right? Theta 2 less than theta 1. It's a smaller angle. So here's, with that in mind, because that always has to be true, here's what we end up saying. We always say less to more bends toward. What the hell does that mean? Well, here's what it means. Less to more, well, come on. Yep. Less to more. Less what to more what? Well, look, here's in this case, the light went from less n to more n. So if you go from a smaller, let's see, light goes from, well, how about this? I'll be as wordy about this as possible. Light goes from a substance with a smaller n to a substance with a bigger n, well, then that light bends toward. How about this? If light goes from a substance with a smaller n to a substance with a bigger n, then light bends toward what? Well, it went toward, oh yeah, the normal. Less to more bends toward is the key to tons and tons of questions on the exam. Okay? Well, I don't know about tons and tons, but certainly multiple questions will deal with your ability to decipher that that phrase. Okay? Okay so far? Okay. Now, we've shown sometimes, we talked at one point about this, and it says, this looks like, that the speed of a wave depends on its frequency and its wavelength, right? It looks like that. Well, but then we said the speed of a wave really is, if we think about the speed of a wave on a string, that depends on the medium it travels through. Of course it does. Same thing for here. Speed of light through a substance depends on the substance, right? It depends on the medium it's traveling through. All right? It's really the wavelength that depends on the other two, because the frequency depends on, I don't know, remember like the shape of a tube, how long a tube is, or it depends on, really, it depends on the source, right? It depends on, with a tuning fork, it depends on how long the tuning fork is. And wavelength then ends up depending on the other two. But what we're trying to get at here is, if we look at a wave that goes from one substance to another, well, some stuff about it in each substance is the same and some is different. Well, for sure, I hope we get that the wave speed in each substance is different. Right? We showed that on that applet. And we defined, we said that n is c over v, therefore v is c over n, and the speed depends entirely on what we call the index of refraction of the substance. All right? The wavelength, and whether or not you'd see it, we did show that. Let me go back here and restart this with an angle of 0 again. Restart. Next step. Next step. Next step. Get rid of all this junk. All this junk. Oops, next step. Get rid of that. Notice. Look at the incoming wave. Pause. Pause. Oh, I can't pause. Well, that's okay. Look at the incoming wave and the outcoming wave. Now, I do have to pause at a careful time. I'll pause like right now. Oh, no. Oh, no. Yeah, I didn't do a great job. But here's here's the wavelength of the stuff. Let me see back. Here's wavelength of the stuff in the first medium, right? Distance between two wavefronts. Here is wavelength of the stuff in the other substance. So wavelength clearly does not stay the same. And it doesn't stay the same because the speed of the wave changes. Okay? So that means we can check off different for wavelength. However, frequency is the same in each. And here's what we mean by that. Well, for one thing, we can look back at that applet and say, how often do wavefronts, hit a boundary, or well, yeah, how often do wavefronts hit the boundary coming from substance 1? And how often do they leave the boundary and enter substance 2? Well, at the same frequency. We can also, I like this one, we say frequency for light is about, if you remember, it's about color, right? So if you're, underwater wearing a red bathing suit, it still looks red underwater. If you're above water, it still looks red. The frequency of that light does not change. That's the easiest way for me to remember that. But that's just me. Now, we can say now, where are we at? Yeah, there's n is c over v. Right now, any wave speed, we can say, is, well, f lambda. And this is also f lambda. Well, this is frequency in a vacuum, lambda in a vacuum, because c is speed of a wave in a vacuum. And, I'm going to write this v is fn lambda n, or the frequency in a substance with index of refraction n. the wavelength of the wave in a substance with index of refraction n. Okay, but remember, the frequencies are the same, so that means these two things can go away. They are equivalent. All right, and what that shows us is that not only is index of refraction a ratio of speeds, it's also a ratio of wavelengths. And what I hope you can remember is that the bigger, so I'm just going to say that here, bigger n means smaller v, and bigger n means smaller wavelength. Faster, well, sorry, the larger an index of refraction, the slower the wave goes. And the slower the wave goes, the more the wave fronts get bunched up together. Okay? Yes, okay, a couple of super important things. One, when we're solving problems with this stuff, always, always, always measure angles from the normal. And this one's kind of like, duh, you know, you just have to be careful about what's your subject, or your substance 1, what's your substance 2. Okay, make sure you keep them straight. Let's look at a couple of, what do you want to call these? There's no math to do here, but just look at a couple of examples of what happens. We've got a triangular prism that's made of glass. Now, the deal is n of a, hey, don't do that. Don't do that. It's supposed to be a surprise. Ah! Jerky. No. Why won't you behave? Now, n of it's going to happen again. N of a vacuum, by definition, is 1. Well, just 1, not even 1.00. It's 1. Because, right, n is c over v, and the speed of a wave in a vacuum, speed of light in a vacuum is c, so it's c over c, and that's 1, right? N of air, it's pretty damn close, maybe, to 1. It's like that. We'll just call it 1. Close enough. All right? N of glass, everything else is bigger than that. Right? It's about, depending on what kind of glass, we'll say it's about 1.5. That's something to know. All right? Well, maybe not, of course, but n is c over v, right? There is nothing, or v is c over n. There's nothing that can be faster than the speed of light in a vacuum. So this has to be less than c. That means this has to be bigger than 1. N is always bigger than 1. Always, always, always. For anything other than a vacuum, of course. All right, so here's what happens. This is a great animation that doesn't work anymore. But when the ray gets to this boundary, moving at a certain speed, a speed that's pretty darn close because it's in air, pretty darn close. So I'm going to say that v here is just about c. Well, here all it does is it keeps going straight through, but it just slows down. All right, so here there's a v that's less than c. Okay? Now, here's where this is just driving me nuts right now that I can't show you this, but when the wave hits that boundary, what I do, notice, is I construct a normal, a nice perpendicular, right where the wave is going to hit that boundary. Right? Now notice, we're going from, the wave is coming from a substance with n equals, let's say, 1.5, and it's going into a substance with n equals 1.0. So this is a 1.5 to 1. This is a more to less. Make sense? 1.5 to 1, bigger to smaller, more to less. And therefore, the light bends while it was going this way, right? It was going that way. Here's the normal. It bends away from the normal, and now it goes, something like in that direction. We can calculate that direction if we know what all these angles are. We'll say forget about the phi and stuff. There's some, forget about that for now. Okay? So again, all that happens here is a change of speed, but not direction. Here, change of speed and direction. Right? This is back to v is just about c. It speeds up. Okay? If we look at this one, I'm sure this will show you what happens ahead of time, which is a huge pain in the butt. But again, so this is traveling. Yep, super. This is light traveling in water, and it enters some sort of crazy triangular air bubble. Now, water, and depending on the, if it's salt water or fresh water, but it's typically 1.33 for n of water. So again, if light comes in here and hits this boundary at a certain speed, well, certainly it's going to be v is less than c. Here it's going to speed up, because the v in here is just about c, just a fraction less than that. And notice, when it hits this boundary, here's what we do again. We construct ourselves a normal, a nice perpendicular to that surface right there. And while the wave was going this way, well, let's see, this is 1.00, this is 1.33. This is a less to more. So notice, the wave was going this way, it bends this way toward the normal. That's a bends toward. Okay? Any of sense? Okay. One problem to do. Well, with several parts. A laser beam incident at an angle of 30 degrees to the vertical in a solution of corn syrup, and water. The beam is refracted to that angle. What's the index of refraction of the syrup solution? So here's what we always draw with this. You draw a boundary between two substances. All right. Now, what they don't say here, which makes this a great first example, I think we can assume that it's coming from air. So let's say that it comes from air into this solution of water and corn syrup, right? And we'll say that it comes in at an angle here, 30 degrees from the normal, from the vertical. You don't need a protractor here, folks. All right? And it bends. It has to bend like that to an angle of 19.24 degrees. It's got to bend toward the normal here because we're going air, n equals 1 to n equals something greater than 1. This is a less to more. It's got to bend toward the normal. All right, we want to find the index of refraction of the solution here. So that means we're going to do, well, I'm going to write it as n air sine theta air is n solution sine theta solution. We're looking for n solution. So n solution is n air sine theta air over sine theta solution. And that's just 1 times the sine of 30 divided by the sine of 19.24. Don't forget those degrees, folks. Those degrees, that degree symbol is a unit. You got to have it if you want full credit. So sine 30 divided by sine 19.24. And I get n solution 1.52. I better darn well get bigger than 1. If I don't, I've done it wrong. Suppose the light's red with a vacuum wavelength. See, the lambda vacuum is 632.8 nanometers. Find the wavelength in this stuff. Well, let's see. N solution is lambda vacuum over lambda solution. Fair enough? That means that lambda solution is lambda vacuum over n solution. So we'll call that 632.8 divided by 1.52. And I get lambda solution is 416, I guess 0.3 nanometers. Right? As we go to a substance with a slower speed, a bigger index of refraction, the wavelength gets shorter. Now the frequency, careful here, the frequency, part C, we can do one of two ways. For sure, we're going to do this. V over lambda. Right? So we can either do V solution lambda solution, or we can do really C over lambda vacuum. Just make sure here you don't mix the two up. You can't mix a vacuum speed with a solution wavelength. So I'm going to use vacuum stuff. 3 times 10 to the 8th is the speed of what do you call it? Light in a vacuum divided by vacuum wavelength 632.8 nano. So I'm saying times 10 to the negative 9th meters. So that is a frequency of 4.74 times 10 to the 14th hertz. And I guess we had to do it that way because we didn't know yet the the speed in the solution. Right there, we're going to say V is C over N. So that's 3, 8 divided by 1.52. 4, 1.97 times 10 to the 8th meters per second. Okay, folks. So that's all the that's the vast majority of the mathematical stuff with refraction. What we do with this is we now start to talk about lenses and how lenses make light bend to then form images. So we'll get back into ray diagramming with lenses, but now we have the sort of foundation as to why it happens. Okay? All right, folks. See you tomorrow.